Josh, if you end up with the I, do you still want the approximate?
You don't need to do the approximate if you get to the I.
Okay.
No need. Okay. Any other questions?
Can you do number 6?
I can try. Let me see if we have the same number 6.
No.
What is it?
It's 2x squared plus 8 equals negative 3x plus 1.
So this is in the solving quadratic equation section. Was it negative 3x or negative 3x squared? Is that just this? All right, so you're trying to solve this quadratic equation? This is right?
Yeah.
Okay. So what did you do?
I moved everything over.
Okay.
So I did 2x squared plus 3x plus 7. I went ahead and did the...
I agree. And then did you try and factor it or didn't work?
I think I did, but it didn't work out. So I did x equals negative 3 plus minus square root 9 minus 4 times 2 times 7 over 2 times 2.
That's right.
And then I got x equals negative 3 plus minus square root 9 minus 56 over 4.
Yep.
And then I got x equals negative 3 plus minus square root negative 47 over 4. And then my answer was negative 3 plus minus I 47.
Root 47.
Oh, yeah, root 47 over 4. Is that correct?
That's good. Is that not the keys answer?
Well, just like the I kind of like throws me off, and like I get very worried because I know like you said cover the negative sign where the 4 is. On the other step.
Mhm.
Yes. And so like I get
Cover the
very,
negative sign.
very worried when I'm multiplying my numbers as to what sign it's going to be. So like when some like when I covered it, I got a positive number. So automatically I assume that's negative, right? Because now I'm putting down that
Yeah.
minus sign.
Mm-hmm.
And if I cover it and it's a negative,
Then it'll be
down,
positive.
It'll become positive.
That's right.
Okay.
Now there are some other ways that you can look at it. Like you're always going to have negative 4, right? Just imagine this piece in here. You're always going to have negative 4. Then you're going to have 2 numbers, right? Always. Let's look at all the possible cases we could have. I'm just going to make up numbers, right? 2 and 3. 2 and negative 3. Negative 2 and 3. Let me do this one up here. Negative 2 and negative 3. Are there any other cases I could have? They can both be positive, both be negative. This one could be positive, this one could be negative, this one could be negative, this one could be positive, right? Do y'all see what I'm doing here? Let's look at the answers for each of these. If you cover up the negative, this would be negative and negative, which is positive, and then 4, which was positive again. But then I'm subtracting it. So do you agree this would turn out to be a negative number? I'm doing this for a reason, you'll see in a second. This one right here, covered up, these are all positive, and then you're going to subtract. So this would be minus. Cover this up, you would have what? Those would go together to be a negative, but then you're subtracting it, so it would be plus, and then you could have this case here where you would have what? Negative, and then subtract it, and you would have plus. Now, the reason I'm showing this to you is because some people just get into a habit of just counting how many negatives they have. You know, I mean, you can kind of see here. If you have 2 negatives, right? Just look at this whole expression. Do you see 2 minus signs? You see 2 minus signs? It's going to be positive. If you see 1 minus sign or 3 minus signs. So those are odd, right? If you see an odd number of minus signs, it's going to be negative. If you see an even number, then it's going to be positive. You can just do that if you want something simple, not to even have to think about it. So like here, how many minus signs do you see? Just 1. So it's odd, that's going to be negative. All right, let's get to today's stuff. And what did I say we were going to do today? We were going to graph quadratic functions. And I gave you a 7-step procedure last class. And I said that's what we would start with, right? So you're probably very excited about this. All right, so let's start with, I think I'll make one up. 2x squared minus 8x minus 3. Oh, sorry, I forgot to put f of x here in front. And the instructions here are to sketch this. Now, when we say sketch, that means we want a pretty good picture. Doesn't have to be perfect. We're not trying to land a man on the moon here. Okay, it doesn't have to be that precise, but the picture needs to look pretty close to what it is. All right? So what was the first step? I'll number my steps here as I go through. Make sure it is a quadratic function. Is it?
Yes.
Yes, it is a quadratic function. Second thing. Okay, is this, what did y'all say? I thought you said concave up, concave down. That's a calculus term. Did someone say that? No? Okay, good. All right, concave up, concave down. That's the precise way to say it in Cal 1. But okay, so it's going to go up here. Why? A is 2, right? A is 2, which is positive, and anytime we have positive, we know this little parabola is going to go like that. So I just draw a little picture of what it's going to do. You can say up if you want. The picture is fine also. And on your test, this is what I'm looking for, you know. I'm looking to give you partial credit, so you want to show as much work as possible. 3. Vertex. And how do we find the vertex? Yeah, it's going to give us, the vertex is a point, right? HK. And to find H, I'm going to go over here. We just do negative b over 2 times a. What would negative b be for us here? 8. And I forgot to label this. You don't have to do this at the beginning of the problem, but some of you might find it useful at the very beginning just to kind of write down what A, B, and C are. Again, that's not a necessary step, but you're going to need those things anyway, right, throughout the problem. Okay, so it's positive 8 over 2 times what? 2, which is 8 over 4, which is 2. Now that's nice, what? 2 is a nice number. In examples as we move on, be prepared for these to be fractions, all right? And then things get a little bit nasty. All right, how do we find k? And I hadn't ever done an example, right? But I told you all you do is you plug h into the function. And h for us was what? 2. So that means plug 2 into the function. Does everyone understand that if you get h wrong, k is going to be wrong, right? Most likely. I mean, you could get lucky and. Pardon me? Okay, in the formula, this is a negative b, right? Negative b, and if b is already negative, it changes it to positive. All right, so let's plug 2 into the function. So I'm going to replace all my x's with 2's, right? There it is. And order of operations and all that, we've done this already. 2 squared, right, goes first. And that's 4, then times 2. So that gives me 8. And then I do this multiplication before I do the subtraction, right? So minus 16 and then minus 3. What's that? Negative 11. So what I can tell you right now is that my vertex is the point 2, negative 11. Right? That's my vertex. And we didn't call on names last time, so let's see. Sir, I have a question. Since you don't have your name tag, I'll ask you. What was your name again?
Zach.
Zach. All right, Zach. Were you here last time? Oh, then I'm asking.
Been here 3 days, sir.
Okay, yeah, all right. Then I probably, did you watch the videos? You did? Okay, so maybe you'll be able to do this. 2, -11 is going to be where on this picture? On that graph, where is that going to be? 2, -11. It's a point on our graph, right? It's our vertex. So what is it? Where is it? Any ideas? No? Anybody? Say it in words. Just tell me like in layman's terms. You're trying to explain to someone, oh, that point's going to be center, lowest point. Good. Okay, that's going to be the lowest point. Do you agree with that? Because it opens up, we know that that point is that point right there, right? That's the lowest point on our graph. As far as the work, though, we're done, right, for step 2? Okay. Step 3, sorry. What's step 4? What's that? Quick sketch. All right, so that means I'm just going to real quickly draw an X and Y axes. I'm going to plot this point, but very, very loosely. That means 2 to the right, down 11. So my vertex is down there. See how loose I am with that? I don't even care to like count it. I just know it's over and down. And my graph opens which way? Up. Now why am I doing this? Why am I doing this sketch? To see how many x-intercepts I have. And in this case, I do have them, don't I?
2.
I have 2 x-intercepts. So I have 2 x-intercepts. Those are exclamation points, okay? I'm telling myself, I have 2. So what is step 5? Or is it still part of step 4? Sorry. Someone read step 4 to me. Do you have the steps right there?
Quick sketch 5 is how many?
Okay, so 5 is how many x-intercepts do we have? So I should have written that down. Step 5. How many x-intercepts? We said 2, right? If we have 2, go find them, right? If we have 1 or none, we move on. So how do we find the 2 x-intercepts? This is still part of step 5. We set the function equal to 0, right? So I'm going to set the function equal to 0, which means I'm going to set 2x squared minus 8x minus 3 equal to 0. Because I have 2, I need to find them. This is how I find them. I set the function equal to 0. And now I can either factor that, or if it doesn't factor, use a quadratic formula. And I know for sure I should get 2 answers. If I don't get 2 answers, I've done something wrong somewhere, right? Because this shows I should have 2. So x is negative b. What's negative b? 8 plus or minus the square root of 64 minus 4 times a times c, right? Did anybody get the tattoo? Nobody did? Maybe this weekend. There's your quadratic formula. All over what? 2 times 2, right? Okay, did y'all like that thing where we count the signs, or y'all just want to do the number? Doesn't matter to me. You don't care? You do it whichever way you want. Okay, I'll do it both ways. Cover up the negative. 4 times 2, 8 times negative 3. Negative 24, right? And then I'm going to subtract it. So I'm going to wind up adding 24 to 64. I continue. So I have x must equal 8 plus or minus square root 64 plus 24 over 4. So this is where, if you want to do it the other way, you would just say, okay, how many negative signs do I see here? I see 2 of them. If you see an even number, then it's positive. If it's an odd number, it's negative. All right, now this is 8 plus or minus square root of 88 over 4. Hey, doesn't 4 go into 88 and 4 goes into 8? Am I allowed to just take the 4 and do that? No. Remember the rule. You have to do everything up here first, then you can come in with the 4. You cannot do this 4 into that 8. You cannot do that. All right? Do y'all understand why you can't do that? Let me just ask you a quick question. Let me do it this way. Isn't this the same as 5 over 4? This is 5 over 4, isn't it? But if you think that you can just do that, then you're really saying that this is equal to what? 1? 5 over 4 is not 1, right? So that doesn't make sense to do that. Okay, so what do? I look, can I simplify square root of 88? Well, it's not a perfect square, right? So at this point, if you can't break this down, right, we would just leave it as it is. But I think you can pull some stuff out, can't you? But you don't have to. And let me tell you why you don't have to in this problem. Okay, so what I'm getting at is you could break that down to be like what, 4 times 22. Then you could split that up, square root of 4, square root of 22. Then you can make that 2 root 22, couldn't you? And the 22 doesn't break down. So we could do that right here, couldn't we? But we're not going to. The reason is because what are we trying to find? X-intercepts. And those are things I'm going to plot on a number line, right? Does anybody know what this number is just by looking? No, right? This is why the approximation on our calculator of square root of 88 is as good as trying to do that on a calculator. It's going to be the same answer, exactly. So we may as well at this point get our calculators out and take the square root of 88. Go ahead and do that. And you should get, like, what is it? 9.38. And everyone will ask me, how many decimals should we go? Look, 2 decimal points or 2 decimal places, that's fine. All that divided by 4. All right. This is where I did this step right here. Remember this? I'm going to look at the plus and the minus now. Get my 2 answers. I do 8 plus 9.38 divided by 4. 8 minus 9.38 divided by 4. I'm waiting for you to do that on your calculator. Oh, my microphone fell. Okay. Who has the top one? Anyone? 4 point what? 3.4. Okay. And the other one? Negative 0.34. Anybody agree? Anybody agree? Yes? All right. That should be good. Questions? All right. We have found the x-intercepts. So now we move on, right? Was it -3? Okay. Step 6. What's step 6? Y-intercept. And how do we find the y-intercept? you plug 0 into the function, which is always, as long as the quadratic is written this way, it's always just going to be what number? Or what? It'll be that constant at the end, won't it? Because the x's are going to go to 0. It's going to kill everything off except that -3, which is c, isn't it? C is -3, a is 2, b is -8, c is -3. So in this case, it's -3. All right, step 6 done. We good? Plot it. Now that's the last step, right? All right, so here we go. Now here's where my graph needs to kind of look decent, all right? So here's my x and y axes. I'll go ahead and label them x and y. You could also write up here instead of y, f of x, either way. All right, so I'm going to start with the first piece of information I had, which was my vertex. My vertex was 2, -11. 1, 2, sorry, 1, 2, and then -11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, -11. Somewhere around here. And I'm going to label the point like that. The next piece of information, yeah? It is positive to -11. I don't know why I did that. To +11, or to -11. Thank you. The next information that I gathered was the x-intercept, right? These two things. So 4.34, that's bigger than 4, right? It's less than 4.5, 4.5. So this is why people always ask me, well, how many decimal points do I need to go, right? Like on this, there's no sense in going like 5 decimal places because it's hard enough to graph 4.3, right? 4.34, nobody's going to get that good, right? Unless we've got like rulers and, you know, we've blown everything up real big. So let's see, 4.5's here, 4.3, I don't know, ballpark it, somewhere around there. Can we be happy with that? What I will do is I will label it by making the point 4.34, comma 0. Remember, it's an x-intercept, so the y-coordinate's always 0 at that point. The other x-intercept is at -0.34. So here's -1. -0.34, I'm thinking is right about here. And it's -0.340. Any other information I need to put on the graph? The y-intercept, or my y-intercept was at 0, -3. So if I go 0, -3, 1, 2, 3 here, that point lives on my graph. I will label that point 0, -3. And now I have all the points, right? That's all the information I have. Now, one thing we didn't really talk about last class is that when you have these parabolas, regardless of whether or not they open up or down, both of them will have a vertex, right? And if you can imagine this, it's an imaginary line extending down through the vertex like this. Okay? That is technically called the axis of symmetry, which we're not going to really, I'm not going to ask you about that. But the important thing about the axis of symmetry is that this parabola, if you were to reflect it over that dotted line, is a mirror image of itself. So what's happening here on the left is identical to what's happening on the right. It's not possible to get a parabola that looks like this. It goes up like that, and then on this side does this. That is not a parabola. All right? It's got to be symmetric across that imaginary line. So when you draw this, it needs to look symmetric as best as you can do, right? And also, it needs to be a U and not a V. All right? Cannot come down to a point in a corner, all right? Yeah, you need to round it out because This is a different graph, okay? That graph is the absolute value function. It's not a quadratic function. So the way I like to do this is I like to kind of round it off first. I just kind of round it a little bit like this, just to give myself a start. And then from there, I'm just going to go out the left side and it's just connect the dots at this point. You know, something like that. Woo. And on the right side, the same sort of thing. And you just kind of take a step back and you go, yeah, it's good enough. All right? We're done. Yes?
Domain and range.
Yeah, we're not gonna discuss that too much at all. Yeah, on some of the, oh, well, you know what, do they talk about domain range? Oh, you know what, hold on. I take that back. Let's do domain and range. It'll be easy. It'll be easy to talk about. The thing is, we didn't talk technically about domain and range before when we were talking about functions. So we can do it. It's not that bad. Okay, if you go back when we first started talking about functions, domain are the inputs and range are the outputs. These are the x's, these are the y's. All right. So let me explain how we can do this. Remember that this parabola, imagine it keeps going up and going out forever, right? Going up and out forever, out the roof of the building, and just keeps getting wider, doesn't it? So this domain thing is saying, what are you allowed to plug into the function? What are you allowed to plug in? Well, the good news is with all parabolas, there are no restrictions. You can plug anything you want into a parabola. You can plug in the number 2, it's going to spit out a number. You can plug in 3, it's going to spit out a number. You can plug in 4, it's going to spit out a number, right? If I plug in the number 10, is it going to spit out a number? Yeah, somewhere up there, right? So when it comes to this problem, the domain of it, and the domain of all parabolas, is going to be all real numbers. All real numbers. Now there are several ways to say this. That's one way. Another way is to write, I don't know if you've ever seen this, a double struck capital R. That means all real numbers. Another way to write it is what's called interval notation, negative infinity to positive infinity, which means everything on the number line in both directions. And then you can also put x is greater than negative infinity, less than positive infinity. So this is almost the same thing, except you're saying that your x's that you can plug in can be bigger than negative infinity and less than positive infinity, which means everything. That's the domain for all parabolas. Now, the range, on the other hand, are the outputs. So think about the y coordinates. Let's just look, I'm just going to pick a spot right here, this y coordinate. Does my graph ever achieve this y value? Imagine going straight across here. Here and here, don't I get to that y value? Yes? How about if I move down a little bit? Do I get to that y value? Yes? How about here? Here? Yeah, because remember the graph keeps going, right? Here? How about if I go up like, 3,000 feet? Yes? How about down here? No, because I have a lowest point, right? The lowest point's down here. What's the lowest y value I ever have? Negative 11. Right, is the lowest y value? So do you agree that the range of this, the outputs, have to be bigger than negative 11? So how I write that is like this. The range is y must be bigger than or equal to negative 11. That's one way to write it. Does that make sense to you? The outputs, the y values must be greater than or equal to 11. Bigger than means going this way. Another way, in what's called interval notation, you could write -11 to infinity. Now, I don't want to get into this too much, this interval notation, but if you're familiar with it, you can use it, all right? I'd have to spend 30 minutes talking about interval notation if I really wanted to get into it. Just use this one, and you're good. Any questions?
Are you going to put that on the test where we have to write it, the range and domain, or?
I'm more inclined to just ask you to sketch it, steps 1 through 7. Yeah. But as far as interpreting these things, we will, because there's application word problems coming up, we do need to kind of understand what the range is. For example, if we motivated the whole idea of parabolas by taking like a ball and throwing the ball through the air, actually did it with markers, right? Then that point right there, right, would represent the highest point of the ball being thrown through the air. So in terms of like a range, this is the highest point, right? Understand? So we don't need to technically be thinking range, but we need to understand that the highest point has something to do with the range. All right. I'm going to do one more, and then I'm going to let you do one, all right? We're going to sketch this. F of x equals 3x squared minus 7x plus 2. Okay, Amber, you're up. What's the first? You're going to do the first 2 steps for me, Amber.
Make sure it's a.
Okay, is it?
Yeah.
Okay. Second step. Okay, so what does this one do? Okay, why is it going to go up? That's right. Good. Okay. This number is greater than 0. It opens up. And we move on to Gerald. You're up, Gerald. Take your time. And you're still writing some down, or you want me to? We're good?
Step 3, yeah.
Okay.
Finding the vertex.
Okay.
So step H is negative b over 2a. So in this one, it'd be positive 7 over 2 times 3, which would be 6.
Good. Good. Okay, so you're doing positive 7 divided by 2 times that number, which gives you 6. And then that's H, right, Gerald? And then what do you do with that to get K?
You have to plug, make the function, and then you put that number set of 6.
Into the quadratic, right? And okay, so this is where things get a little rough for people. It's 3 times 7/6 squared minus 7 times 7/6 plus 2. And Erica, what is that? I'm just kidding with you. It's a mess. It's messy, right? Okay, so look, there's different approaches you can take here, all right? We could work with this all as fractions. In other words, we could square 7 over 6, which would give us, what, 49 over 36, wouldn't it? And then multiply that times 3, and then figure out what this is, and then get a common denominator and put them all together. Couldn't we do that? I mean, it would take a while, but we could do that. But at the end of the day, what is K? H and K give us a point, don't they? And just like with the x-intercepts, It's hard to graph the radicals. It's hard to graph fractions too. So we want this to be a decimal at the end, don't we? So let's go ahead and start now with decimals. So what is 7 divided by 6 on your calculator? What is it? 1.166666. Uh-oh. So we'll just go 1.16. How about that? We're approximating it. Squared minus 7 times 1.16 plus 2. Did you figure it out?
Yeah.
Okay. All right, so at this point, I'm saying that this was equal to this. Now this is approximately this, because I've now approximated with the decimal. And that is just like an order of operations problem. Square this guy first, and then multiply it times 3. When I do this part right here, I get 4.0368. You could say 4.04. That's good enough. Or you could say 4.03. That's not going to affect the answer too much. Minus, and then 7 times 1.16. Get about 8.12 plus 2. That's going to be ballpark area of what it is. So what are y'all thinking? Negative 2.08 or 2.09? All right. If you're within a couple of hundredths of this, 0.8 or 0.9 or 0.7, that's fine. Pardon?
I got 2.1.
10.1?
Negative 2.1.
Yeah, that'd work. I mean, remember you're going to plot this, right? Do you think you're going to be able to tell the difference between negative 2.1 and negative 2.08 on the graph? No, right? But you'll want to label it. And when I'm grading these, I'll see your work and I'll know, you're a little off with the rounding. That's why it's an approximation, right? All right, so remember, as a vertex, the vertex is a point, right? It's going to be 1.16, negative 2.08. That's my vertex. Yes?
So I have a nifty y equals.
Yes?
If I do all of the steps, can I trace it and check it?
Yeah, you can check your work with that. Yes.
So it was different.
What was different?
I lost it. Never mind.
Okay.
I must have been
You can double check it.
there. Mine was 2.05.
Negative or positive?
Negative 2.05.
Oh, but your calculator is doing a better job of approximating than we are. Because when it's we used 1.16, right? Your calculator probably used 1.166666, probably 10 decimal places minimum, and did the same thing here. And then when they did all that work, so, I mean, that's why I'm saying it's going to be off a little bit, right? It's going to be off a little bit.
But if I still show my steps.
Yes, just show me your work. Look, I've had students before, believe it or not, on a test where this is the problem given, right? And I'm not kidding you, this is the answer that they give me. Exactly what I'm going to put up here on the board. They draw a box. And you know what that is? That's their answer. That's all they'll put. That's the screen you're looking at when you graph it.
Right.
That's it. They type in their calculator, this right here, and then it graphs it, and that's exactly what they give me. And that is a sketch of that quadratic function, right? You will get 0 points for that. 0 points. Yes, it's a little off, but our picture is going to be better than that picture because it's going to have all the labels of where everything is, right? What I'm getting at by this is that, and I think we talked about it a little bit, is that if I could say, hey, everybody go buy this $150 calculator, right? Everyone, that's a required part of the class, is that everyone buys that $150 calculator, even though this is the last math class you ever have to take, then we would all be graphing using that. And we'd be using all the features of the calculator to do it for us. But that's not the case. So what's most important for us is the work. That's the part of it that we need to see. All right. Where are we? We're moving up here. You already know what the next step is, right? All right. Daniela, you're up. I don't know what to do. I forgot what I'm doing up here. Quick sketch. Why are we doing that? To see if we have x-intercepts, right? Okay. So when I do this quick sketch, Daniela, what am I putting on here? What's the first part I'm going to put onto this sketch? Okay. So I'm on step 4 here. And my vertex was 1 point, and then down to, so to the right and down again, right? Like this. And which way does it open, Danielle? Up. So if I draw a U going up like this, then it's going to hit, yes? Twice? So we have 2 x-intercepts. That's the answer to 5. 2 x-intercepts. So this is exactly like the last problem, isn't it? Exactly like the last problem. Where are we at? Bianca, you've been out for a while. You okay? All right. So you want to help us with what we do for step 5 now?
Step 5.
Mm-hmm.
Is that how many x-intercepts?
Yep. So we already know we have 2 from this, right? And then since we have 2, what are we going to do? Mm-hmm.
Of x equal to 0.
Okay, good. And our f of x was, because I erased it, 2x squared minus 7x plus 3, right? Equals 0. Was that it? Okay, so we set that equals 0. What was that? Oh, 3x up out here and 2 out here. Okay, I apologize. All right, now Bianca, I'm going to stick with you. Not to pick on you, but I want to see, since you missed, if you were able to get on track here. How would you do this?
Start plugging that into that.
You can use this, yes. You're free to use this, right? Now, let's just take a quick vote. How many of you think that you're just going to go directly to this? Yeah? Anybody going to try and factor it first? Okay, so this is where you have personal preference. In the previous problem, it would not have factored. This one does. This one actually, 3 and 2 is 6, and negative 7, and the 2 numbers are negative 6 and negative 1. So it would work if you did it this way. But the quadratic formula is the fail-safe method. It's going to work every time, right? So I just want to point out that it does factor. But I'll stick with the quadratic since most of you like that. And where are we already? Caesar, you want to go, Caesar? I just want you to tell me what to write in the quadratic formula. Just tell me what I'm going to put in here.
7 plus or minus 49, square root of 49.
Okay.
Minus 4 times 3 times 2 over 2 times 3.
Okay, good. And what is this going to turn out to be in here? Negative 24. So it's going to be minus, right? Okay, good. And what is 49 minus 24, Caesar? No idea? 25? Use 25. And you recognize that, Caesar, right? Square root of 25 as being something nice. So that turns into 5. And so now at this point I can do the 2 different cases. 7 plus 5 over 6, 7 minus 5 over 6. So I'll do that right here. So equals the plus and the minus. 7 plus 5 over 6, 7 minus 5 over 6. What do we got? 2 and 1/3. Which as a decimal is 0.333, but I'll just say 0.33. So those are our two x-intercepts. All right. Where are we? What is it? Step 6. Y-intercepts. Intercept or seps? Singular or plural? Singular, right? We always will only have one y-intercept. One and only one. So step 6, our y-intercept is f of 0, which is 2. Wasn't it? Now the final sketch. Starting with my vertex of 1.16, right? And then down 2.08 or something like that, right? So here's 1, here's 2. Notice that when I'm drawing drawing this, notice that I'm not doing this. I'm not doing like 1, 2, right? Because it's going to be really hard for me to do 1.1 in here, isn't it? And my x-intercepts only go out to 2, right? So my graph's going to be in this little tiny little focused area. Why don't I kind of spread out my vision a little bit? 1 here, 2 here, kind of spread things out. See that? It gives me some room to work with. And down 1, 2, 3. Here's -3. So I was supposed to go out 1.16, somewhere around here, and then down right at about 2. I will label the point 1.16, -2.08, I think we had. Good enough? That look good to you? All right, next thing on here. X-intercepts, which were 2 and 0.333 right here. Man, that doesn't look, it looks, sorry, I'm going to move this over just a little bit. It looks different from this angle than it does straight on. And last thing, y-intercept, which was 2. I forgot to label those points. This is 0, 2. This is 2, 0. And this one right here was 0.330. And I will draw now my parabola, curving out the bottom and bringing it up. Whoa. Whoa. Good enough. So I know as you move through your education, you're going to definitely need to be graphing parabolas, right? So look, here's the most important thing in my eyes about what we're doing. It has nothing to do with parabolas at all. This is a process, right? It's a procedure. It's a 7-step procedure. Can you do a 7-step procedure without like needing a sheet to work off of? Can you kind of get it in your head, run through the process? That's what this is all about, okay? When we were talking about jumping through the hoops, right, to get your college degree, you know, you have 2 people, one with a college degree, one without. That's a college degree right there, okay? All this college degree tells an employer is that you're teachable, that you can learn something, right? And when you take a math class, it's very procedural, it's very analytical, it's very mechanical. And that's a certain way of thinking. And that degree, in some way, shows that you've got a basic knowledge of how to do things like that. Versus without the degree, where it's kind of a gamble. right? You don't know what you're getting unless you know the person. Does that make sense? Okay. Has nothing to do with parabolas and graphing them. Who cares, right? I mean, it's a parabola. Big deal. It's over. I'd rather go look for Pokemon. Pokemons? What's the plural of Pokemon? Pokemon? I'm wondering if I should give you some special cases before we, because I think what we'll do is we'll take a break and come back and do one, let you do one. Let me show you very quickly two special parabolas that you could run into. All right, how about this? F of x equals x squared minus 4x plus 1. So I'm going to run real fast through this, all right? You ready? Here we go. Real fast. It is that. It opens up because it's a 1 here. The vertex is h is negative b, which is positive 4 over 2 times 1, so that's 2. K, when I get that, I plug 2 into the function. I get, let's see, 4 minus 8, that's negative 4 plus 1. So negative 3, so I've got 2 negative 3. Okay, with me? Just you don't have to write all this down. Just think through this. Fourth step, quick sketch. Vertex is 2, 1, 2, negative 3, hold on. Ah, shoot, hold on, I wanted that. You know what? I need this to do something else. Pardon me. Let's make that 7, okay? That's going to change this value. Where's that going to be instead? This doesn't change, all right? If I plug in 2 into this, 4 minus 8, negative 4 plus 3, that's going to be 3 instead, all right? Yes? Where's my vertex? Out 2, up 3? Up here? Which way does it open? Ah, okay. We have no x-intercepts. If I have no x-intercepts, I'm going to move on. 6, y-intercept. What's the y-intercept? That I'm guaranteed. 7. And now I go to a sketch. Chances are you're not going to see one of these on your test because it skips an entire process, doesn't it? Okay, so we go here like this. My vertex is out 2, 1, 2, up 3, 1, 2, 3. Here's my vertex. I have a y-intercept of what? 7, 4, 5, 6, 7. I'm not labeling the points. You understand you would need to do that, right? So how am I going to draw this if that's all I have? I'm going to guesstimate. I'm going to use the fact, remember that axis of symmetry and the mirror image? I kind of have an idea what the left side looks like, don't I? The left side kind of looks like this. So the right side sure as heck isn't going to be this, right? So I can almost, sometimes it helps if you actually draw a dotted line in there. And that helps you kind of gauge distances. Like this distance here has to be the same. This distance here has to be the same. You know, this distance here, that's the same. And so you kind of get that idea of what it does. Understand? Okay, so that's how you do one without, that has no x-intercepts. That would be a special case. One other one I want to show you. Hold on a second here. There. How about that one? X squared minus 4x plus 4. Okay, so it's parabola, right? Opens up, and the vertex h is negative b over 2a, which is 2, K is, what happens when we plug in 2 here? 2, 4, take away 8, add 4, 0, isn't it? Quick sketch would be next. And it's right here, isn't it? And which way does it open? Up. That means we have how many x-intercepts? 1 x-intercept. And what I tell you to do if you have 1 x-intercept? Move on. You already know what it is. If you only have 1 x-intercept, it was the vertex. So you don't need to find it. You already have it, don't you? That's the vertex. That's the only x-intercept you have. And now let's get the y-intercept, which in this case would be 4. Yeah? So when I go to graph it, just like the previous problem, I go out, let's see, 1, 2, here's my vertex, which also happens to be my x-intercept, and my y-intercept is up here at 4. And then I could draw the left side out, and then try and mirror it over and draw something like that, right? So like that, and you're done. Got it? I'm going to give you your break here in 1 minute. Things to be careful with whenever you're going to graph these. And again, this just goes off of the history of me seeing things. What if you're going and you do all your work, steps 1 through 6, and you go to draw your graph, and you get this situation right here. You've got your vertex here, and you've got an x-intercept here, and an x-intercept here. And let's say you have a y-intercept here. Yeah, what does that tell you? Something is wrong. Something in your work is wrong, okay? Do not do this. You're laughing, but trust me, I've seen it, okay? Don't just put dots and then try and connect them together. That's not what this is. Your graph has to look like a parabola at the end. And if something looks off, most likely something in the math is off. All right? Okay, we're going to take a break, and then we're going to come back and we're going to talk about applications, which means word problems. It's on my watch 1:38. I'll be back at 1:48. in your homework, when you're asked to graph these problems, they're going to ask you for the axis of symmetry. And there's not a whole lot to it. Remember I said it was this dotted line that goes like this? And if you remember when we were talking about lines, vertical lines had undefined slopes. So we had a special equation for a vertical line. It was x equals a number. That was the equation. So the x value of this dotted line is h. Right? That's how far you'd go out to get to that dotted line, left and right, would be the h. So when you go to answer that question, all you're going to do is put x equals and then whatever the h is. So like if your h was 2, your axis of symmetry is x equals 2. Understand? That's it. You're done. That is clear? So there's no new thing really, all right? Okay. Now my goal here is to finish applications of quadratic functions. And then next class, the goal would be to come in and try that no-risk exam. Remember we talked about that? Where everyone comes in, I hand them an exam, you sit there and you work on it. Tomorrow. Yeah, but the thing is, if you come in and you're like, you know what, I want to work with my notes and just try this on my own, you can do that, and then come on Thursday and take the test. But if you really want to just try it, like full out try it, and you take it and you feel like you did good, then you don't have to take the test on Thursday. You would take that as your grade, but no notes, right? You have to do it like a test. So I'll separate the room out like a test. Does that sound like a plan? What's up?
When we take the test, are we going to have time to talk about it after, or are we just going to take it and then everyone leaves and then we come back Thursday and take the actual test?
It would depend on how long it takes you, but my guess is it would probably just be everyone takes the test and then leaves. Yeah.
Is it kind of cool to talk about it?
I know it would be, yes, I know. Well, that's why I'm saying, as a class, we need to decide, like, do we want to even try that, or do we just want to do more of like a full day of review tomorrow where maybe I can give you the test, y'all can work on it and we answer questions, but nobody is taking the test?
That sounds cool. Yeah.
Everyone's shaking their head?
Yeah.
So who really wants to try a practice test tomorrow, and if they do good on it, they do good on it? How many people? Okay. Everyone else just wants to review? Okay. Let's plan on just review. I might be able to work out with those people who raise their hand. I might be able to work something out where you go across in the lab and do it. And that way you're not interfering with everyone else in here. But it's just raise your hand again if you know for sure you'd want to really just try the exam tomorrow, full out. Let me count. 1, 2, 3, 4, 5, 6. Okay, those 6, that's it. No one else changed their mind. I can accommodate 6 people across the hallway, but I can't take 13 of them tomorrow. All right? Okay, we'll do that. And then if you're over there and you're trying it and you say, shit, forget this, you can come back over here. All right? And ask questions. All right. So there are so many different applications of quadratic functions. I like to pick one specific one because I think it's most applicable to the real world, and that is falling objects on Earth. So it turns out that if you are standing on the Earth, which you all have done, then you jump up and down, and we have an idea of how long it's going to take to come back down, right? And if I jump off a 5-foot little platform, it's going to take some time for me to get to the ground, right? But if you're on a different planet, or if you're on the moon, gravity is less. And so those videos of these guys on the moon that they're all bouncing around, it's because the gravitational force was about 1/3 of what it is here. So instead of weighing, let's say, 100 pounds on the moon, you would weigh about 30 pounds or so. All right? So you're a lot lighter. So when you jump, you actually go up further and come down, right? Well, objects on the Earth, since we're all subject to the same gravitational force, the way that things fall should be pretty uniform. So I'm going to ask a question here now. Does anybody have a big textbook? I know this class doesn't have one. Someone's got to have a textbook in their backpack. No one? How small? I just need a textbook. I want a little bigger than that. No? That's the only textbook we have. Okay, we'll take it. We'll take it. Yeah, you know, I don't think it's going to matter. Okay, so here we go. You ready, everyone? We're going to run an experiment. I have a small textbook, and I have a piece of paper, and I'm going to drop these two, and we're going to predict which is going to hit the ground first. Ready? You got it in your mind which is going to hit the ground first? Yes? Feel confident with that? Okay. Ready, set, go. All right. Did it happen the way you thought it would happen? Yep. Yes? Okay. So the ground hits the, the ground hits the book. The book hits the ground before the paper. Why? Air resistance, weight. What do y'all think? Any other answers? It's more solid? What do you mean? Like more? The pencil and the book would hit at the same time? Well, I don't know. Let me try that. A pen and a book. Let me do that. So they hit about the same time, right? All right, so here's the deal. It has nothing to do with the weight. The weight has nothing to do with it at all. All right? It has everything to do with the air and the impact that the air has. If you've ever driven down the road at 50 miles an hour, or 80, 85, then you roll down your window and you stick your hand out, you know what happens? You know, right? And then you do that thing for a while. That's pretty cool, right? So that's because the air is like water. You know, you put your hand through water, you feel it. Air is like the same thing. So when you let go of this, the air, it's almost like trying to drop things through water. You know, you've seen them go down through the water like that. The air has more of an impact on this than it does on this. But it has nothing to do with the weight. And I can prove it to you. Right now I can prove it to you. So if you think it's because this is heavier, right? If that's why you think this drops faster, then if I put this paper on top of this and I do not tape it or glue it, just set it on there. If you think it's the weight, then when I drop these, the book should fall away from the paper faster, shouldn't it? If you think it's the weight, okay? All right, so what happened there is that the book moved the air out of the way as it was dropping, and so this was no longer under the influence of the air at all, so it was free to fall without the air slowing it down. Now, here you go. Make sure you sign in before whoever's leaving. Okay, sign in. If your name has a mark on it, don't worry about it, just sign over it. So what we discovered at some point was that since all objects on Earth fall at the same rate and that the air is the only thing that impacts that, well, air is a pretty big deal, right? We can come up with a formula that will tell us how far something should fall after a certain amount of time. All right? So if you take air out of the room or take it out of the atmosphere, which you can't do, right? But if you take it out, everything will fall together. Have you ever seen the video of the guys on the moon when they drop a hammer and a feather at the same time? Anyone ever seen that? They're on the moon and they're videotaping it and they get a hammer and a feather, they drop them, they both hit the ground at the exact same time. The reason is because there's no air on the moon, so there's nothing to slow the feather down. And so it's just to prove the point. We already knew, scientists already proven that. But it was kind of like yeah, like we were telling you for a long time, like the Earth was not the center of the universe, and you didn't believe us, and now, you think that it's weight, and here it is, we're just proving it to you, okay? So if you drop something, just think about this for a second. If you had a building and you were standing here and you wanted to drop something off this building, after the first second, it would go a certain distance, wouldn't it? After another second, would it go the same distance? It's going to travel further in the second than it did in the first second, right? And then in the next second, it's going to travel even further. So it's speeding up as it goes, right? And so it's not linear. It's not like when you get paid, you get so much per hour. So you make $20 an hour. In 2 hours, you make 40. In 3 hours, you make 60, right? It's not linear. It's not 10 feet each second. It increases. Well, it turns out that it is quadratic. And that means that there is a formula for it. And this is the formula. D of t equals negative 16 t squared plus v sub naught, or v naught, or v sub 0. Just put v with the subscript of 0 there, plus d subscript 0. That is it. Now I have to explain to you what all of these things mean, all right, before we can proceed. Does everyone understand that all objects on Earth will fall at the same rate regardless of weight? Yes? If we take the air out, here's the formula for it. So put here no air. Now, I'm going to have a skeptic in here who's going to be like, well, you're taking the air out. That's kind of the whole point. We live on Earth, we have air, right? You can be like, what's the use of this formula if you don't have air, right? How can we use it? I mean, we live in a place where there's air, so we have to take that into account, don't we? Well, the common analogy, you have to learn how to crawl before you walk before you run, right? This is a very simple formula. Now, you want me to put air in there? This formula is not going to be quadratic anymore, and it's not going to be as easy to work with. But you have to start out with something basic. And that's why when you open up a physics book and you look at these formulas, you're like, what the hell is that? It's because they have to take into account everything. If you break it down to the very basic part of it, it can be something as simple as a quadratic. So this is kind of like a base point to start with. Then later on you add in the air. Then later on you add in the humidity. Then later on you add in what the object is, the texture of the object, right? What's the difference between a feather and a piece of paper, right? So there's a lot of dynamic things that could be happening. But it just gets very complicated. So we start here. All right? So let me explain each of these letters up here. First of all, let's start with t. T is time, and it's measured in seconds. And I'm going to put over here what we've been looking at, quadratics, just to try and show you that we have a quadratic function. It just looks different here. T is like the x over here. All right? T is our variable. Seconds. D sub 0 is our initial height, and this is in feet. Initial meaning starting height. So I'm going to take an object and I'm going to drop it. I'm on Earth, there's no air. How high do you want me to drop it from? Whatever that number is that number. What is that over in the common formula that we have here? That's the c, right? It's just a number by itself. Okay, v naught is the initial speed. This is measured in feet per second. And I have to add something to this. If positive, so I'm putting a little plus symbol with the circle around it to represent positive. If it's a positive number, then it's up. If it's a negative number, it's down. Now let me explain what I mean by that, because that is usually confusing to students. I'm gonna do this with markers, okay, because it's easier to understand. If I take this marker and I lift it up, let's say 5 feet off the ground, then d naught, by the way, we say that like this, d naught. D naught, not meaning nothing, meaning 0. Initial starting point, time is 0. That's what that comes from. All right? So if I have this at 5 feet, then d naught is 5, right? And if I just let it go, did it have an initial speed? No, it didn't. I just let it go. So v naught would have been what? 0, and that would have killed off this term completely. Understand? This one I'm going to just let go. This one I'm going to throw down. Which is going to get there first? The one I throw down, right? Okay, I gave it an initial speed, right? And it was downward. Whatever that speed is, if it's a downward speed, you're going to put it in as a negative number. Now, if it's upward, then you're going to put it as a positive. So what if I, the same speed I threw it down with, I throw it up with? Then this one's going to get there afterward, right? So to account for that, it's the plus or the minus there. With me? Okay. What's next? So v naught is like what over here? B, right? It's the B. Now, notice that here, the A is always negative 16. I wonder what that comes from. Why is it always negative 16? What do you think that has to do with? Gravity. That's right. If we're on Earth, this is negative 16. If we're on a different planet, it's a different number. All right? Depending on which planet you're on. So we don't, for falling objects on Earth, we do not have any control over this number. It's always going to be negative 16, which means that if we look at this as a parabola, it opens down, right? Well, that just makes sense, right? It's when you start something, right? Let's say you start from this height, and here's time. If I throw it, or sorry, if I just let it go, it's going to start falling, right? As time goes on, it falls. Boom. I could also have this scenario. I throw it up into the air, right? And then it comes back down. But there's no way to get the parabola to open up. That'd be a weird planet, right? You let it go, it goes up. Like, whoa, shit. Okay, so that's where we are. Now, what is d of t? D of t is exactly the height of the object at t seconds. And it's measured in feet. So the left side of this equation, this right here, always tells you how high the object is at a specific moment in time. As an example, at time equals 0, how high is it? At time equals 0, how high is the object? Not 0. That's what we would plug in for t, wouldn't it be? What would it be? At time is 0, how high is the object off the ground according to this formula? At time is 0, how high is it? Whatever that is, right? D naught. Because we plug in t as 0, that's gone, and all we're left with is this. What about how high is the object at t equals 1? Well, we'd have to plug 1 in and figure out what the answer is, right? The important thing to note is that the left side tells you how high your object is after some given point in time. And I believe that's everything. All right, so that's the general formula. The things that we always need to determine in the word problem are these two things. Before we can even start, we must know what those are. If we don't know what those are, we can't do the problem. So you ready to start? Example. A ball is thrown upward from a 200-foot bridge with a speed of 20 feet per second. I'll draw a picture. I like pictures. You like pictures? This is a bridge. There's a guy standing on the bridge. And he's going to throw a ball up. It's going to go up and it's going to come back down, but it's not going to hit the bridge. It's going to go down and hit the ground, okay? Got the idea? Throw this ball up. It's going to go up and come down. Here are the questions. First, how high does the ball go? B, when does it reach maximum height? C, when does it hit the ground? And D, when is it 50 feet off the ground? Some of the word problems in the homework start off by just giving you a quadratic function and asking you questions. If it's a falling object on Earth problem, it's gonna be phrased something like this. All right? So just keep in mind, we're only talking right now about falling objects on Earth. All right, so we all know that since it's an object falling on Earth, it must follow that formula. The formula looks like this: d of t equals negative 16 t squared plus v naught t plus d naught, right? That's our formula. I told you that we have to know what v naught and d naught were in order to do the problem. Do we know either one of those? Yes? What are they?
V is 20.
V naught is 20. Is it positive or negative? Positive, because the ball was thrown upward. And d naught is, how high was that bridge? 200. We're assuming it's thrown from 200 feet. Now, you could say, well, wait, if the person was holding it, it was a little bit higher than the ground. Let's just agree it was from 200 feet, it went up, okay? All right, so now what I'd like to do is I'd like to rewrite this formula, replacing V naught and D naught with the actual values, and then we can start answering the questions. So up here, I'll write the function. D of t equals negative 16t squared plus 20t plus 200. Yes? Questions? The next thing I'm going to tell you is probably the most important thing I could tell you the entire semester. I mean, the most important, but let's just wait for a second. She's not even paying attention. Never mind. Okay. Which way does this parabola open?
Down.
Down, right? So I know if I draw this, it's going to open down, right? And because of the word problem, the way it's phrased, if I'm assuming that this thing opens down like this, then this point's really important, isn't it? That would represent the highest point, right? So look at this. When it says, how high does the ball go? What is it really asking for? The whole vertex? The highest point, right? It's the y value of the vertex. Right? Remember, this is a point, h, k. Isn't k The distance from here to here? Yes? And remember, on this graph, instead of having a variable of x, what's our variable? T, right? Time is this way. And then up here, this is our what? Distance? That's our height. So we've got height is the y-axis, and time is the x-axis. So when they're asking how high does the ball go, that's just a hidden way of saying for us to find k, isn't it? But we know we can't find k unless we find h, right? When does the ball reach its maximum height? When? Time. At what point in time does it reach the maximum height? What would that be? That would be the h of the vertex, wouldn't it be? So this is really just a secret way of asking you for the h coordinate of the vertex, or the axis of symmetry. When does it hit the ground? When? Time, right? When? Time. When does it hit the ground? Well, let's draw it where it's hit the ground. Here and what? Back here somewhere? But wait a minute, that would be like negative time, wouldn't it? And we would probably throw that answer out. If we got two x-intercepts, we'd throw one of them out because one of them wouldn't make sense. The other one, well, the ball's only going to hit the ground that first time. It might bounce, but yes? Okay. All right, so this really is a hidden way of asking you to find the what? X-intercepts. Now, I'm going to say x-intercepts because that's what we're familiar with. But technically, we would call these the t-intercepts because t is the variable. But we'll say x-intercepts. When is it 50 feet off the ground? This one's the hardest one to interpret. When is it 50 feet? Let's say 50 feet's right here, right? The question is, this is 50, what's this, right? What do you plug in to get 50? 50 is the output, right? What you're going to do is you're going to take this function, exactly, and you're going to set it equal to 50. Do you remember what you do to find the x-intercepts? You set the function equal to what? 0. Because you're saying, okay, when is the ball at 0? If I say when is the ball 50, you're going to set the function equal to 50. If I say when is the ball 100 feet off the ground, you're going to take the function, set it equal to 100. Now, I don't think I'm going to work through this. This is a take-home quiz. All right? You just got to finish all the work. I already told you all you have to do, right? So you need to go home, you need to find h and k, put them in there. Just make sure that you answer the problem with the correct units. Like this, I'll give you help on the first one. Whatever this number is, your answer should be that number feet, right? And then the next one should be, you think through the next, okay? Do you think you can handle that? That's due next class at the beginning. All right, let's work through another problem. All right, can we do that? Yes?
Okay, so this might seem a little irrelevant. Do you just automatically assume that whatever you're throwing will reach a height of 0 at some point? Because like if you're throwing off the bridge, technically it could land on the bridge, but are we just assuming for the sake of the problem that...
For the sake of the problem, I'm throwing the ball in a way which it will come off the bridge and then go down and hit the ground. Which actually brings a more profound question into play here. This is a pretty big deal. Let's say I take these two markers and I drop them exactly the same time. They will both hit the ground exactly the same time, right? Yeah, we all agree? All right. So what if I take this marker in my left hand and I drop it, and at the exact same time I take this marker and throw it that way, horizontally, as fast as I can? Which one will hit the ground first? The one that I drop and it just falls, or the one that I throw and it goes that way as it falls? What do you think? What do you think is going to happen? The one I drop is going to hit the ground first? Okay. Any other predictions? What's that? The one I throw is going to hit first. No, I'm not going to throw it down, right? I'm going to throw it like straight across, okay? And I'm not going to throw it up because then obviously it would take longer, right?
We say you got to throw this first.
Horizontally, as hard as I can horizontally.
I think they would both hit the same ground at the same time.
Same time, okay? So I think most people will say either the one I drop will hit the ground first, or they'll say the one that they'll go together. And some people think that the one I throw will get there faster. So we have all three cases, right? Everyone's got different opinions? All right, so let's just try. It's not going to be a very good experiment. This is no way scientific at all. All right? Just listen for them, okay? It's close, right? Well, I can tell you that if you do it properly, in a proper scientific method, which when I was in high school, I had a great physics teacher who had rigged up a dart gun, okay, like a Nerf gun or something. And he had it that when he pulled the trigger, the dart went out, and simultaneously it was attached to a string, and it dropped a dart at the same time. And we would listen for it. And it turns out that you can show that they both hit the ground at the exact same time. And what that means is that horizontal speed has no effect on how fast how long it takes you to hit the ground. That's pretty amazing. So if you were to sit here, right, and let's say you were standing, you are highly impressed with my stick figures, aren't you? All right, so I'm sitting here and I have a gun, all right? And I take this gun and I shoot a bullet out of this gun. One bullet, but that just represents the bullet path, the bullet's path, okay? If I shoot that bullet out and it hits a target downrange, right? That's what happens. If I were to sit there and shoot that bullet out and drop a bullet at the same time, which one hits the ground first? You already know the answer. Same time. So when you shoot a bullet, right, and you drop one, it's already hit the ground. That's how long it took. Same amount of time for that bullet. The reason why you don't get that drop is because this thing's going so fast that it's traveling as a parabola, okay? Now, if you don't shoot it out very fast, it's just going to go bloop, and it'll just go like that, right? And this is going to be a parabola. But if you shoot it out really fast, then it's still going to drop like a parabola, all right? It's just that it's going to be way down there because it's going out there faster, so it takes less time. It's going out faster. So as you go out, this distance dropped is less because it's already that far away. Does that make sense? So these, snipers that shoot things from like 300, 400, 500 yards away, they have to account for that drop. They also have to account for a lot of other things, right? But the main thing is the fact that there's going to be bullet drop. Is it possible, because the Earth is round, right? I mean, the Earth is not a straight line like that. Like, we don't stand here. It looks like it's flat, but it's not. Is it possible that you could shoot a bullet fast enough that as it's going out and as it's starting to come down, the Earth is curving away? What do you think? Imagine I shot something so fast that the curvature of the Earth, it starts falling, but the Earth starts curving away from it as it's falling. Does that seem weird? Do you know what's up here above us right now all over the place? Your GPS requires them. Satellites, right? These are things that are going around the Earth, right? They're just floating around the Earth. What's that? They are doing this. We shoot them out there at a certain speed, and then we turn off the rockets, and what's happening is that they start to fall towards the Earth, but the Earth starts to curve away from them, and they get stuck in this continuous falling motion. And that is what orbit is around a planet. And that's what our satellites are doing. Now, if you can get them, so imagine these things are falling around the Earth. If you can get them just perfect, the Earth is turning, right? Let's say the Earth is turning. If you can get them perfectly aligned and at the right speed, then they will not only be falling, but they will actually be going at the same speed as the Earth is turning. And then you have stationary satellites that sit over the same spot all the time. So they're always over Texas, right? I forget what those called, geosynchronous satellites or something like that. So there are satellites that do move around, go across the United States, and there are satellites that just sit in one place. But all of them are in this continuous perpetual free fall. And it's just, does that make sense? It's pretty cool? No, not really? Just to me? Sorry. All right. I have about 15 minutes. All right, this is my last example, and this is going to be also on your take-home quiz. All right? Second problem. Now, I've been using this example for a long time. I usually do it to keep people like involved in the lecture, kind of like the kids on the bus thing, I know. So y'all are going to think I'm still very morbid when I do this, but all right, here goes. It's almost September 11th. We're getting close, right? We're getting close. Does anybody know how tall those buildings were? Okay, anyone has the permission to get on your phone real quick and just look it up. I know you can do it. You can find 2 Pokemons in 10 minutes. I'm sure you can figure out how tall the World Trade Center was in less than 20 seconds. I'm disappointed. I'm really disappointed. I thought y'all would have been done.
That's too slow.
Too slow? What's that? 1,776 feet. I think it was 120 stories. All right, that's probably measuring to like the top satellite antenna or something like that. Who cares? Okay? So look, please understand, this is in no way meant to be disrespectful or meant to be, offend anyone, especially because I'm recording this. I don't want someone throwing this back in my face. But, sometimes you have to think about tough things. So my daughter was asking me the other day, she said, let's play this game. I forget what it was called. Basically, like, what would you prefer? To be able to fly or be invisible, and then would you rather be able to fly or be invisible, all this stuff, right? And then somehow it got into, and I know it's going to sound like my family's morbid too. Somehow it turned into, would you rather die by fire or by ice? Would you rather freeze to death or burn to death? That was one of them. Okay, what do y'all think? No, if you had to choose, freeze. I think I'd go with freeze too. Yeah.
It takes like 30
I heard it.
Like after 30 seconds, you don't feel the burn. Like
Are you sure about that?
Well, my started as a firefighter.
Really? I don't know about that, man. I don't trust that. I don't trust that. You may not feel it. Okay, maybe you don't feel it because it's burned all your nerves away.
Like by the time you're just freaking out.
That's a long 30 seconds. That's a long 30 seconds, though. Okay, so look, freezing, I've heard feels like knives in you and stuff. And okay, look. So, look at that day, right? People had to make decisions, right? Some people had to make a decision of basically, are they going to go by fire or are they going to go by jumping off the building, right? So, how long was that fall? Yes?
We're assuming they're jumping off the top, right?
No, let's not do that because they weren't all the way up there, right? Most of them were on about the 110th floor or so. So let's just make this an easier number to work with. Let's just put it at, 1,200 feet, okay? 1,200 feet. Now, if you don't like this example, just imagine a rock being dropped off a 1,200-foot building, okay? That's the same question we're asking. How long does it take that rock to fall? All right. Person jumps out of 1,200-foot building. A, what's the max height? B, when is the max height? Same questions as the problem before. C, what was C? When did it hit the ground? When do they hit the ground? Yes.
Do you want the D of when at H?
Pardon me?
Do we want the D?
Do we want the D?
When at whatever height you specified, what time would they be?
Oh, no, that last one. Sorry, part D. Part D. No, we'll just leave it at this one. Okay? So look, in the last problem, I said a ball was thrown upward at a certain speed, right? I missed something big, I guess.
So sad.
Should I have missed it?
Yeah.
Okay, thank you. Okay, thank you. All I said was, okay, never mind. I'll go back and look at it. I'll go back and look at it. All right. So, in the last problem, I said the ball was thrown upward with a speed of 20 feet per second from a 200-foot bridge. In this problem, I have not given you that much information, have I? All I've given you is the height, which is 1,200 feet. That number represents what? D naught, right? D sub 0. What are we missing? Yeah, the initial speed. So this comes down to that thing with, dropping the pen. Do I just drop it? Do I throw it down? Do I throw it up? Person jumping out of a building. I mean, who knows, right? Who knows? We can just say probably 0 initial velocity, just like dropping a marker. So is that fair if we all agree upon that? All right. Do you think you can answer these questions? I think you can, as a take-home quiz. Here's what I find pretty remarkable, and we're going to end lecture here in just a second. I'm going to look at my phone to do something. I'm going to calculate something real quick. Okay, that's all right. I'm going to take this number instead. Yeah. All right, so here's what I'm going to end on. Your answer for how long it takes to hit the ground should be greater than 8 seconds and less than 11 or 12 seconds. So it should be somewhere between 8 and 12 seconds. All right? I'm just giving you a range. If you look back at the video of this, not of people jumping, but of the building actually coming down, have you ever watched it? Like, I know a lot of us try and avoid it, but have you ever thought that, man, it takes a while for it to come down, or does it seem like it comes down fast? What do you think? It does pretty quick. If you look at the footage, how long it takes the building to fall, it's about the same amount of time, really close, to a rock being dropped right next to it. Now, what is amazing about that is that when you drop a rock, the only thing acting on it is gravity, right? And it'll take the rock, let's say, 11 seconds to fall. What I'm telling you is that the building took the same amount of time as the rock. Don't you think it should have taken longer? Doesn't it have to actually destroy itself as it compresses down, right? Think about, I don't know if you've ever put your hands on an I-beam that is like an I-beam, like those metal I-beams that they put in this, in the World Trade Center. Just the mass there, the amount of structural force you had there. The forces involved for that thing to come down. I'm saying this because I've always found it's totally mind-boggling the amount of force that was released when that building fell. so much force that it can compress itself down to nothing as fast as just a rock falling next to it. There was just so much energy that all those huge columns of concrete and metal rebar were nothing. They couldn't stop the gravitational energy pulling that building down. You would think, you know, towards the end there was some stuff left at the bottom, but most of it came down. Amazing, amazing amounts of energy in that. Pardon?
The momentum of everything?
Yeah.
Keeps
Just that
building.
it was that one floor. Once that first floor fell, everything above it, all that force, and then everything else after that was done. Unless you're a conspiracy theorist or something like that. Okay, these two problems are due next class at the beginning. We will review, except for 6 people. When it comes to the applications, do the homework, okay, just to get practice. But I can tell you right now that on the test, I'm going to give you a problem with falling objects. That's what will be on the test. Okay, everyone have a good day. Sorry about being so morbid. I'm not trying to, but...